My name is Daniel Mazin, and I will be talking about extragalactic background light, Hubble constant, and the intergalactic magnetic field. And first of all, thanks the organizers for inviting me. And this is the outline of the next 20 minutes or so. So I will be talking about the extragalactic background light and what's the relation between the gamma rays we are detecting and extragalactic background light, and how do we use it to study cosmology. And then I'll tell you where we stand and what are the perspectives for the next future, and the future is bright. So what we have here is we have gamma rays, very high energy gamma rays, and we're using propagation effects in order to not so much to study what is happening in these AGNs. Of course, there is an entire community of scientists, of astronomers who like to understand what exactly is happening in these extragalactic sources, how the gamma rays are produced. But here, for the sake of this presentation, this is not the topic. It's not very interesting how exactly the gamma rays are produced. Interesting is that they are produced millions of light years away from the Earth, and then they have to propagate through the universe. The universe is not empty. The universe is filled with different backgrounds, and CMB is of course the strongest background. But the second strongest background in the universe is called extragalactic background light, and it's the accumulated light from all the stars and galaxies in the universe. So once they started burning, they released the photons, and maybe they don't burn anymore. Most of them don't burn anymore, but they release the photons, and this is a homogeneous photon field. This is that's filling the universe. And now the gamma rays do not have enough energy to do a pair production with CMB. Of course, CMB is stronger, but the energy of CMB is not strong enough to do an electron-positron pair production with the gamma rays. However, this extragalactic background light, this one has enough energy in order to do a pair production. So here, what is happening is that a part of this very high or high energy gamma rays is absorbed by the extragalactic background light, and then you have a signature, kind of an absorption signature in the spectra of the very high energy gamma rays from distant sources that you measure on Earth, and this the signature depends on the distance to the source, obviously, and on the density of the extragalactic background light. So that's the main idea here. Here, as the energy distribution of this background field, so the CMB is obviously the strongest one, and the EVL is this accumulated emission from all the stars and galaxies in the universe, and part of the optical near-infrared emission of the stars is absorbed within the galaxies and then re-emitted at higher wavelengths. This is what we call dust here, and then obviously is redshifted depending when this emission was emitted. So this is why these peaks are relatively broad. And then if you look how this accumulates over the years, so this is how in the co-moving frame you see this EBL, how it accumulated. So somewhere it started maybe here, and then the peak in the star formation is somewhere between redshift 1 and 2. So it goes up, and then it dilutes, because it's not. Of course, you always add stars, so you always add sources to the extragalactic background light, because you have new stars and new emission from the old stars contributing to it. However, the universe is expanding, and the density of this background field is diluting, and the evolution of this extragalactic background light is very much related to to the cosmology, to the expansion of the universe, and also, of course, to the history of formation of the galaxies and how they evolved, how the dust evolved in galaxies, and so on. And measuring this extragalactic background light directly is very challenging because everything is emitting in infrared and optical. If you try to launch a satellite and to measure it, you typically measure 1,000 times higher radiation in this wave band from the zodiacal light, and the zodiacal light, which is very local phenomena from our sun, reflection from some dust grains in a solar system, and the extragalactic part which you are looking for somewhere here, zodiacal light is somewhere there. So you have to reduce your data by a factor of 1,000 in order to find the extragalactic component. There are some ideas to launch a satellite outside of our solar system in order to measure this extragalactic component from outside of our solar system, but it's very expensive and is not going to happen soon. However, what you can derive directly is the light from the sources that you can resolve. So you see a lot of galaxies, you see a lot of stars. So you can say, okay, this is at least what we can resolve, and the background light is from the sources. So if you take the galaxies and stars you can resolve, and you calculate the mean intensity, then you get to this red points, and this is so-called galaxy counts. So the level of extragalactic background light should not be lower than this red line. There can, of course, be additional contribution to the background light from sources that are not resolved by Hubble Space Telescope, by Spitzer, by whoever. And that's then the question where we are. And now we come here with this Cherenkov telescope. So this is just a picture of La Palma. These are relatively big telescopes. These are like 17-meter diameter telescopes of a previous generation. The new generation is this one, is 23-meter diameter, and measuring gamma rays. Measuring gamma rays in through a Cherenkov effect, not directly, but through a reaction with the atmosphere. Not very important for this presentation. Important is that this technique is sensitive to gamma rays somewhere between, let's say, 20 GeV and some 100 TeV. This is sensitivity of these instruments if you look to certain sources. The current sensitivity of the telescopes like MAGIC or Veritas or HESS is somewhere there, and from the new generation will be like factor of 10 better. Okay, so then what you calculate is, as I say, propagation effect of these gamma rays to their on their way to Earth, and you calculate the optical depth. The optical depth tau is an integral. Straightforward, you integrate over the distance to the source, you integrate over the angle between the photons, the high energy photon from this gamma ray source, and random angle from the background photon, which is this mu, and then you integrate over the density of the background photons and the cross section of the pair production, which has some threshold, and then you integrate to infinity. And then you can calculate the transparency, or the E to minus tau. And then if the source is close by, then E to minus tau, your absorption looks like this. So this is for close by sources. E to minus tau equal 1 means there is no absorption. And if E to minus tau is very small, then basically everything is absorbed. You don't observe anything on Earth anymore. And this is, as you can see, very much dependent on the distance to the source. Okay. So this is the basic idea. And then how do we derive constraints, indirect constraints of this extragalactic background light, which is very difficult to detect directly. So you start just to walk you through let's say the state-of-the-art methods to derive the limits. So you do a likelihood ratio analysis by starting assuming the energy spectrum of the gamma ray source, which can be typically is non-thermal radiation from some blazar or gamma ray burst, which is kind of a log parabola or a power law as a function of energy. Then you fold it with the EBL model, extragalactic background light model, so you know that part of it is absorbed. Then you fold it with the effective area of your telescope, which is of course a function of energy. Then you have an energy migration matrix, because the energy of the gamma rays that you're measuring is not necessarily directly the energies which are emitted by the source. There is a certain smearing effect. And then you fold it with the effective time of your observation, and then you get a distribution of excess events as a function of energy of these gamma rays. And then what you do is you compare the expected number of gamma ray distribution with the one you measure from the source. And by this comparison, you minimize the free parameters which are unknown of this gamma ray source that emits the gamma rays. And then you do this for many sources, because you may have, I don't know, 10, 20, 30, 100 different gamma ray sources at different redshifts. But the EBL is the same. And then you can minimize the function, and you can run this analysis for different EBL scaling. So you say, okay, this EBL model here. It has some unknown parameters of normalization, and then you can repeat your analysis for different normalization factor of the EBL, and then you get a chi-square distribution, which typically has some minimum, and then you can invert this chi-square distribution as a function of the extragalactic background light scale to compute the test statistics value. So you compare a certain chi-square value at a given EBL scale, you compare it with hypothesis that there is no EBL at all. Okay, so then you get something, and in this current analysis, this test statistics value is more than 10. So you first you measure the EBL indirectly with this method, and secondly, you can also show that there is EBL at all. So there is actually a measurement of the absorption of the gamma rays. And it's an example of the result for a given source, which is at a given redshift. You have this test statistic for different hypotheses of what the intrinsic spectrum of this source was, whether it was a log parabola, power law spectrum, or whatever. And then you can translate this limit into the EBL allowed band. As you can see here in blue is what you get statistically from just a single gamma ray source. This would be constrained on the extragalactic background light normalization statistically, and then if you include systematic uncertainty, you get the orange band. So as you can see, it works very well on a, let's say, factor of maybe 50% uncertainty, which is quite remarkably given just a single source. You can take many of these gamma ray sources, and then you can constrain the extragalactic background light density more precisely. So the previous slide was showing you a study from 2016. This is now, let's say, a state-of-the-art constraint using many sources, where you measure the optical depth for TV gamma rays, and this optical depth depends on the extragalactic background light density, which you then can translate into the density of the band, the allowed band of the EBL density. And as you can see, so this band, I mean, what do we learn from this? Here, what we learn first is that this very indirect way of constraining the density of this extragalactic light is very close to the sign points, and the sign points are the EBL reconstructed from the galaxy counts. So it is the resolved part of the EBL, which suggests that if there are additional sources to the EBL, yes, they can be, but they are not that significant. There is not much more sources out there which are not resolved by Spitzer or Hubble space telescopes. That's the message we are delivering here. Also concerning exotic contribution to the EBL, like decay of dark matter. And also that some of the claims of the direct measurement of the extragalactic background light, which were here, that this seems to be excluded. Okay. Now, what about the EBL models, which are depending on the cosmological models? This is the state-of-the-art model, which is shown here in black, with the uncertainty on the model shown in blue. And again, well, this particular type of models, they are constructed using the data from the resolved galaxies. Now, this is not surprising that the EBL model is basically on top of the red points. This is again from the galaxy counts. So the red points here are the same. Oh, sorry, are the same as cyan points here. So this is from the minimum level of the EBL from the galaxy counts, and the EBL models, theoretical models, they reproduce it very well, and then are in agreement very much with the indirect constraints from this Cherenkov data from extragalactic sources. Now, how can we use these constraints? I mean, we can say, fine, there is maybe just a little room of some, let's say, whatever, maximum 2 to 5 nanowatt per square meter per steradian that is allowed to be on top of the resolved sources. Where can it come from? For instance, it can come from population 3 stars, these very first stars that we don't find anymore because they are all burned. However, they have to be there with the zero metallicity. And they only contribute to the extragalactic background light as a diffuse background. They are not resolved sources anymore. And yeah, you can start constraining the population of these POP3 stars in comparison to the star formation rate history of the resolved sources. So the star formation history is the peak around 2, and how it goes there beyond 2, it's a bit unclear. But however, with these indirect constraints, we can study that. Another possibility is that there is an additional contribution to the extragalactic background light from decay of dark matter particle, and in particular from axion-like particles. There are 2 different studies saying, okay, this missing EBL, and what's missing? It means between what the gamma ray data tells us that is possible and the resolved EBL from the galaxy counts. So this extra contribution can be from the decay of dark matter. There is only very little room where this dark matter can be coming from. So in this study, they were finding some little corner where the axion-like particles can be coming from. So the mass would be around 10 electron volt or 8 electron volt. And in this study, there was like a small corner between 3 and 4 electron volt with a certain density. So it's a possibility to use these methods for. The other interesting point is that the community that is trying to measure the extragalactic background light directly is a very active community, and with the new data, it's basically all new data. And it's still like factor of 3 higher than the EBL models or the EBL constraints coming from the TV data. So where this difference is coming from is still unclear. Of course, one can always argue that the subtraction of the zodiacal light is not done correctly, and this is still some kind of artifact of the actual data that they measured, which is 3 orders of magnitude higher. But these are very different type of instruments, very different groups of people working on them, and all of them getting kind of consistent data here, which is like factor of 3 higher than the resolved galaxy counts which is represented by the lines here. So it's still controversial where it's coming from. The other thing what you could do, and this is now even more related to cosmology, is that you can invert the problem. You can say, okay, we did resolve the EBL. Let's say the EBL is what we show here. That's the EBL. Then if that's the EBL, then the optical depth for the gamma rays that you measure is a direct measurement of the distance of the source. Then it becomes clear that from the measurement of the optical depth for the gamma rays, you measure the distance to the source. And this measurement is basically the measurement of the Hubble constant in this integral here, because the optical depth is, as I said, is a threefold integral over the distance over the angles between the photons that are interacting and of their cross section and the density of the EBL. So now if the density of the EBL is known, you can say that this one is unknown, and this mainly depends on the Hubble constant. And the most recent result is that if you assume that the EBL density is known, then you are getting a Hubble constant in the range of 67.5 kilometers per second per megaparsec. And it's using, let's say, late data, because this is close by universe. And it's interestingly very close to the measurements from the early universe with different methods. Okay. Here, the systematic of this study is pretty high, so we can discuss it in the questions section. Another topic that maybe in the next couple of minutes I would like to discuss with you is the potential measurement of the extragalactic magnetic field. Now let's go back to the propagation effects. So here you have a gamma ray source. It emits the gamma rays that go towards Earth. The gamma rays are absorbed by the EBL photons. They produce electron-positron pairs, and in what I discussed so far, this gamma ray is completely lost. So we just forget about it. Okay. Here we do not forget about it. We're asking ourselves a question: what is happening with these electron-positron pairs? And an idea here is this high energy electron-positron pairs, they start producing a cascade. What they do, they basically lose their energy through inverse Compton scattering of cosmic microwave background. This time, obviously, cosmic microwave background is a high density photon field. There is no threshold of this reaction, so the CMB photons are upscattered to very high energies. And then you're getting secondary photons, secondary gamma ray photons into your detector. And how much you're getting here depends on the magnetic field, which is in the voids between the galaxies. Now, if there is no magnetic field at all, you're getting the signal from the same direction. If the magnetic field is in a certain range, then you're getting a halo around the source where the gamma rays are produced. So you're getting, this is not a point source anymore. It will be extended. If the magnetic field is very strong, then you don't get secondary emission at all, because all these electrons and positrons are completely isotropized. And there's a relatively active field in trying to use the gamma ray observation to look for the secondary emission from the gamma rays, and trying to understand whether we can measure the magnetic field in the voids. The parameter space is huge, because it's really unclear whether there is a magnetic field in the voids and what's the strength. There are certain constraints on the magnetic field. So the constraints are here in a cyan color. This is the strength of the magnetic field. You see the possible parameter space are many orders of magnitudes. And that's the correlation length. That means the size of the cell where the magnetic field stays more or less constant, or stays constant. And then depending on the production mechanism of this IGMF, you may find the extragalactic magnetic field in this range, or here. And there are now two studies, so that just to give you an idea what you are getting. So this very recent work, so you're using data from GRB 1901, 14, whatever. in gamma rays. So this is this gamma ray signal from this gamma ray burst as a function of time. So the gamma ray the gammas are decaying, or the flux is decaying with time. And we measured this one with two different instruments, with MAGIC in the range between 300 GeV and 1 TeV, and with Fermi-Lat at low energies. So now one can speculate that the signal, or at least partial signal, in the Fermi-Lat detector at low energies is not from the primary gamma rays, which are produced directly at the JRB location, but there are secondary gamma rays due to the these electron-positron pairs, which are produced through the EBL absorption, but then upscattering the CMB. So this could be potentially this one here, 10 to 4 seconds after the GRB explosion, might be attributed to the secondary emission due to to this cascade. And since it came from the same direction, it means the magnetic field strength must be very small, or no magnetic field at all. So then you're getting B field, which is smaller than 10 to minus 21. Of course, one can also argue that this point is consistent with the primary emission. But okay, so just to give you an idea where we stand. It's another source here, GRB 221009 something, which was measured by LASSO at very high energies, let's say whatever, 10 TeV or 50 TeV. And then it was also measured by Fermi-Lat at, let's say, sub-GeV regime. And different lines are prediction for the secondary emission due to the cascade, which happened on the way to Earth, upscattering of CB photons. And depending on the magnetic field, you should get less or more of the secondary photons. And then you compare what you are getting with what you measured. The measured emission is in black points. And then since you can start excluding these fields or these lines, and these lines means no magnetic field or very low magnetic field. So here, if this is attributed to the secondary emission, it must be larger than 10 to minus 19. An interesting point here is that there is no agreement in the community whether the inverse Compton scattering will be the dominant effect in the energy loss of these electron-positron pairs. There is a group of people who are saying that this is a plasma, and the electron-positrons will be losing their energy in heating up the plasma rather than in inverse Compton scattering. And if this is the case, then there will be no inverse Compton scattering at all, and you don't get secondary emission at all. Okay, so disputed, but anyway. So then, okay, then the next generation of the gamma ray instruments is the Cherenkov telescope array. A lot of telescopes in two different sites. One is in La Palma, the other one is in Chile. And I already tried to introduce you the energy sensitivity of this new array. So it's a factor of maybe 5 to 10 better than the one of the existing Cherenkov instruments. And it's progressing. So maybe in a couple of years from now, we will be starting seeing this high energy span of this technique and the better sensitivity. So all this EBL, Hubble constant measurements, as well as extragalactic magnetic field measurements will become better. So basically with CTA, it's not only possible to determine the EBL density at redshift 0, but you can resolve the EBL density as a function of the redshift up to 2. So then I think I will stop here by saying that this indirect technique works very well using gamma rays in order to study the extragalactic background field and study the let's say observational cosmology through producing constraints on the EBL models, and to studying the possible measurement of the Hubble constant. And there are now quite strong development in the intergalactic magnetic field measurement, which might be possible. Thank you very much.